All right, this is the lecture for section 9.3 on the parabola. I will go ahead and move forward here. We've previously been talking in this chapter about conic sections and analytic geometry, and we've already discussed the ellipse and the hyperbola. So the last one that we're going to discuss in this chapter before our test is the parabola. Okay, so the objectives for this particular section are to graph parabolas with vertices at the origin. We will write equations of parabolas in standard form. Of course, we got to graph parabolas that are not centered at the origin or with their vertices at the origin. And then we'll solve one applied problem. So let's go ahead and move forward. I think. Okay, so if you're following along with your note sheets, the first thing you come to are just some pictures that I found online of parabolas in various cases here. So the first one is actually an ice formation, and the second one is an example of the parabola in architecture. And let me just grab my pen here and get ready to start rocking and rolling with that. So we can see here in this first picture how the ice is tunneled out with the water in a parabolic shape. And then architecture makes a lot of use of the parabola because of its strength. So I'm sure if you've done any sort of studying of architecture or anything like that, you know that the arch is one of the strongest structures you can use. So this building actually has parabolas that go all the way around. It's a pretty cool looking building. And then finally, we have the pattern of a dolphin jumping out of the water. And this is true. This is not just some hokey little picture that somebody drew. Their ascent and descent back to the water have been measured as parabolas. So that's a true thing there, not just someone trying to shove nature into mathematics. All right, so you have previously studied parabolas, but you've studied them from their algebraic perspective. And we spend quite a bit of time in chapter 2 of this same textbook going through all of the outs and ins of looking at parabolas from an algebraic standpoint. So just so you know, or so that it will jog your memory, you can look at the equation of a line and know that you're dealing with a parabola or a quadratic when the degree is 2. So if you notice, I've circled the parts that are squared there in both of those equations. And these are two forms of the same exact thing. This is what most textbooks refer to as the vertex form of the parabola, because the vertex comes in the form of HK that you get from the equation there. Your book refers to that as standard form. But then again, they also refer to what we're going to look at in a moment as standard form. But every other textbook that I've taught out of calls that first form, y equals a times x minus h squared plus k, vertex form, because the vertex is sitting there for the taking. And then I've always heard this form as standard form. That the second equation is also in the form of a quadratic trinomial. So we have different methods of graphing using either form. some of the important things that you need to remember is that if A is greater than 0, that thing opens up. So that would be the picture on the left there. A would be greater than 0. A less than 0 or A negative, in other words, then you're looking at a parabola that opens downward. Hopefully you remember from your studies that these things always open up or down, which is kind of unique with how we're going to look at it today, in that if you come from the perspective of a conic section and slicing that conic section off at an angle to create that parabola, then you'll notice when we get into the material that not only can you have a parabola that is symmetric to the y-axis, but you can also have them symmetric to the x-axis. And we didn't study these before because in college algebra our focus is the study of functions. And you can see here, if you take those parabolas that look like they've been dumped on their sides there, they fail the vertical line test miserably. However, like I said, if we come at it from a perspective of conic sections, then we can allow for this in our studies. So I'll move forward from there. Okay, so we're going to open the meat, I guess, of this lesson with the geometric definition of a parabola. Let me remind y'all, if y'all have any questions at any time, do not hesitate to raise your hand, talk on the microphone, type something in the chat. I'll try my best to keep an eye on the chat window there. And of course, I'll ask you to give me the green check and the red X when you're ready to move on. All right, so here we come from the conic perspective, conic section perspective for the parabola. So we have a new way of defining it. Now it's the same exact thing, it's just a different way of looking at it. So the parabola is the set of all points in the plane that are equidistant from a fixed line, which is called the directrix. And if you're ever typing that word directrix, just prepare to be annoyed because Word does not recognize that particular word. I had lots of fun trying to type these notes out for y'all. So it's equidistant from the directrix and a fixed point, which you can probably assume that is called the focus, just like it is with the ellipse and with the hyperbola. So this middle picture right here really gives us a better idea of what that's talking about. So this dotted line that is on, I'll call it the underside of the parabola, I guess. The outside may be a better way to say that. It's outside the parabola. And then your focus is always going to live inside your parabola. So if you take the distance, if you drop a plumb line basically from the parabola to the directrix, that's going to fall at a 90-degree angle. And if you do so, the distance from the directrix to the parabola and the distance from the focus, okay, I'm going to try to do one of these to the side. Whew, that was tough. The distance from the focus to the parabola are equal. So you can see I have set up right here D1 equals D2 there. So you could move further down or back towards the vertex on the parabola, and you're going to have the same phenomenon happening. So if I drop a line to the directrix here, I am guaranteed that because this thing forms a parabola, that is the same distance from the parabola to the focus as it is from the parabola to the directrix. And then I found this cool picture online that shows all of your conic sections taken out of a cone. So you can see here the circle would be cutting horizontally, like directly across the diameter of the cone there at any point, and you can see it forms that circle. So off to the side, that would be if you were looking down on that cut across, this is how it would look. So the ellipse also goes through the entire cone, but it goes through at an angle to produce the elliptical shape. The parabola has to intersect the opening at the bottom of the cone, and it does so on an angle to create that parabolic shape. And then the hyperbola cuts vertically down so that it actually cuts at a 90-degree angle to the base of the cone. So hopefully that picture has helped you kind of visualize all these conic shapes. Now we're going to look back at this little D1 equals D2 there, and we're going to derive the equation for the parabola from it. So I am going to use this picture that I've marked up here, so let me clean it off. It's a little easier to see. And we're going to do so by using simply the distance formula. So if I am told, or I'm guaranteed with the definition of this parabola, that these two distances are equal, then I can put this distance here and here in terms of the distance formula. So just at the top here, the general distance formula, distance equals the square root of x2 minus x1 squared plus y2 minus y1 squared. So that's the general, pardon me, distance formula. However, we've named, in general terms, we've named the points that make up the endpoints of those segments. So I can use the coordinates that we've named here in my distance formula. So the distance for that length 1 is the square root of, okay, so I'm going to take x minus negative p, x minus negative p squared plus y minus y squared. So let me just highlight where these came from. So we had our x minus our negative p there. So those are my x values being subtracted. And then y minus y. The reason it's y minus y is because they are lying at the same y value. So you can tell that by the horizontal line connecting them, or dotted line connecting them, that they have the same y value. So that's my distance 1, and that is equal to my distance 2. Okay, so I'll do this one in green. All right, so I have x minus p, okay, so the square root of x minus p squared plus y minus 0. squared. And now it is simply a matter of simplifying this all the way down. So first of all, this x minus negative p is really x plus p squared. So I'm just going to start the simplification process. X plus p squared plus y minus y is just 0. That's a 0. Squared equals the square root of x minus p squared plus, well, y minus 0 is just y, so that last term is just y squared. All right, further simplifying. Square root of x plus p squared equals square root of x minus p squared plus y squared. Well, I want to get all of this business out from under that square root so I can actually work with it. So I'm going to square both sides. And when you square a square root, those are inverse operations of each other, so it goes away. On this left-hand side, I'm left with x plus p squared, and that equals x minus p squared plus y squared. Now, I need to do some distribution here. So this x plus p squared is really x plus p times x plus p. And this is x minus p times x minus p plus y squared. So here's the distribution that I need to do. X times x times p times x, p times p, x times x times negative p times x, and negative p times negative p. All right, so once you do that multiplication and simplify for the sake of space here, I end up with x squared plus 2xp plus p squared equals x squared minus 2xp plus p squared plus y squared. All right, so if I came back and subtracted x squared off of both sides, they would both go away. And I can also subtract p squared off of both sides. I'm just cleaning it up here. Those both make 0 pairs. And so now I'm left with 2xp equals negative 2xp plus y squared. And if I add 2xp to both sides, sorry, I'm having to write tiny, I'm about to run out of room, plus 2xp, I'll write off to the side here what we end up with. So when I add the 2xp to both sides, I get 4xp is equal to y squared. And that is how we come up with one of the standard equations for the parabola. So let me get a green check or a red X if you followed my gibberish off to the left there. Jessica and Mike say they're good, and it looks like the green checks are rolling in. Courtney, are you with us? Excellent. Okay, I'll go ahead and move forward. Okay, so this slide just has the formulas that you're needing, and there's a lot I'm going to point out on here because there's a lot that we have to know how to find and calculate with these. So notice, when you have y squared equaling the 4px, and by the way, if we would have derived it the other way, we'd have x squared equals 4py. But when your y variable is the one that is squared, you will be opening either right or left. And that should make sense to you because when we start moving into equations that aren't functions, like the circle, we get y squaring. Ellipse has y squared in it. That's where those basically sideways parabolas come from. When x squared is what you're dealing with, then you're working with something that opens up or down. Okay? All right, let's go back to the y squared version of it. So opening left or right. And the way we say that it opens left or right is that it has x-axis symmetry. Or that the x-axis is the axis of symmetry. That's another way of saying. Now, if p is greater than 0, so this p right here, if p is greater than 0, then this thing is going to open right. If p is less than 0, then that means this thing is going to open to the left. Okay, so when we have the parabola in the y squared form, the directrix, so that line that lies outside of the parabola that is part of that whole distance thing to the parabola, the equation of that line is x equals negative p. So this right here would definitely, this page right here, when you go to take your test, you will definitely want this page in front of you because it's hard to memorize. Okay, if it's y squared, then x equals negative p is the directrix, p0 is the focus. This will definitely be a page of reference for you for taking your test. The focus, like I said earlier, always lies within or inside the parabola. And when we're dealing with the y squared version of it, we can see that the focus lies on the x-axis, so it comes in the form of an x-intercept. So p, 0 are the coordinates of the focus. And then this last one just tells you, okay, so this is the equation of that parabola there. All right, let me go ahead and move on to the x squared version of the parabola. Everybody cool? 1, 2, 3, 4. Mike says yes. All right. Good deal. So we're ready to talk about x squared version. And it's really just me pointing out this stuff, and then we'll dig in on the next slide and start working with these formulas. All right. So when you have the x squared version of the parabola, your directrix is a horizontal line. It lies outside of the parabola. So that's why you have y equals negative p. Since y equals is a horizontal line. The focus also lies inside, but notice the focus is now on the y-axis. So the coordinates are 0, p. And then we have just the equation that we have up top there. So with this version of the parabola, it has y-axis symmetry. And if p is greater than 0, then this thing is opening up. And if p is less than 0, this thing opens downward. All right. Since y'all were okay with the y squared, I'm going to assume you're okay with the x squared and move forward. Stop me if you need for me to recap anything. Okay. let's go ahead and solve some problems with this. Okay, so I'm just going to jot down, since we don't have it in front of us to look at, all of the information for, oh, hang on just a second. Did I put that in the wrong? I did. I skipped a problem. Let me see if I put it later on. I'm sorry. Okay, let me change this equation up here, because we're not here yet, and I want to go in order of your notes. So we'll do it. We'll do this information. Goodness, I skipped a whole section of notes, it looks like. Okay, well we'll deal. All right, so this equation should be y squared equals 8x. So that's what you should be seeing on your notes as the problem at hand. And let me just jot down some information that we know about y squared. When the parabola is in the form y squared, the equation for it is going to be y squared equals 4px. The focus is going to be in the form of p0. Don't forget, when we're in y squared, we're either opening right or we're opening left. And that focus is on the x-axis there. That's why it's P0. And the directrix, or the equation for the directrix, is given by x equals, because it's a vertical line, negative p. Okay, so that's all the information from the last slide. And now we'll use that to first find the focus and the directrix of the parabola, and then we'll graph the parabola. All right, so we have to find the value for P before we can plug it in and say what the focus is and use it to find the equation for the directrix. So I am going to use the fact that I know that y squared is equal to 4px. So if you look up here at our equation, we have that y squared is equal to 8x. So I can say, well, I'm going to replace this y squared on the left side with what I've already named y squared in the general form of the equation. So I get 4px is equal to 8x. Give me a green check if you're okay with that magical swap that I just did. 3. Courtney's typing something, so let me see what she has to say. And I'll draw some lines that may help, might answer your question before you ask it. So 4px is equal to y squared. So I was able to plug it in where I originally saw y squared in the other equation. Okay, I think Courtney's typing. Oh, I got it. Okay, very good. Excellent. I thought that might help. Okay, so now I am looking for P, so I'm just going to begin solving this for P. So I'm going to divide off 4x from both sides. My 4's divide out there and my x's divide out there. My x's divide here, and I'm left with 8 divided by 4, which is 2. So I find in this case that P is equal to 2. So I can go ahead and say, from this information alone, my focus is 2, 0. The equation for my directrix is x equals negative 2. And from there, I can move further and get a couple of other points on the parabola. But let me go ahead and graph what I've got going on here. All right, so my directrix is x equals negative 2. So that's just a vertical line going through the x-axis at negative 2. So there's my directrix. My focus is 2, 0. So my vertex has to be equidistant from my directrix and my focus. So my vertex of the parabola is right at the origin, 0, 0, because I've got 2 units in either direction before I hit the directrix or the focus. Now, I need to find a couple of other points because 3 points determine a parabola. Well, I know that this thing is going to be opening to the right. So if I choose any x values that are greater than 0, I know I'm going to get out y values that are on the parabola. And I'm just going to use the focus value for x there, which is 2. That'll set me up nicely. So I already know that y squared is equal to 8x. That's the equation of my parabola. And I'm going to see what I get out when I plug in 2 for x. Well, y squared is equal to 16. I take the square root of both sides, and y is equal to positive or negative 4. Don't forget, you've got to take both cases into account there. Because when I have this equation, y squared is 16, that is asking me, what can I multiply by itself to make 16? Well, I can multiply 4 by itself to make 16, or I can multiply negative 4 by itself to make 16. So I've got 2 points here. I've got the point 2, negative 4, and I've got the point 2, positive 4. So 2, negative 4, 1, 2, 3, 4 is about right here. 2, positive 4 is here. I've got my vertex. I'm ready to graph my parabola. That's it. So we've got, let me just point out our important information here. We have our focus and our directrix that we got from finding P. And then I was able to take that information, place it onto the graph my vertex from there, and then I found a couple of other points that satisfied the equation. Green check if you're ready to move forward. Green check, green check, green check. Courtney's typing. So we'll wait to see what she has to say. And I'll take a big old gulp of water. Where did the negative 2 from the x come from? Hang on just a second. That's an easy one to answer. Okay, I am told in my general information, let me get a nice bright color to point this out. And I'm going to get a thicker pen so you can see it. We're told that when we're in the y squared form of our parabola, that the directrix is given by the equation x equals negative p. So this is x equals negative p, and I found out that p was 2. So x equals -2 is the equation of that directrix. Did that help, Courtney? Excellent. I see the green check. We'll move forward. Oh, actually, we don't need to move forward. I need to erase this slide and use it again. And for those of you that, actually, I'm going to have to make this window bigger. Okay, let me go back. All right, for those of you that are following along with the notes that I typed out, the next, I completely left out the box that talks about the latus rectum. That sounds awful, doesn't it? I kept giggling when I was doing these notes. That's how mature your professor is. All right, so I'll just use the picture that we already have drawn here on the graph to describe the latus rectum. The latus rectum, okay, Mike's typing something, so I'm sure it has something to do with latus rectum. Okay, so the latus rectum is the line segment. Get my mind out of the gutter. Unfortunately, Mike, it stays there most of the time. I do not have the purest of thoughts. Okay, so the latus rectum is simply the line segment that connects one side of the parabola to the other that goes through the focus. And let me just highlight the focus since I drew over it with a pretty thick pen. There's the focus. So the latus rectum touches the parabola going through the focus. And the information that we miss from the slide that I forgot to put into the presentation here that's on your notes is that the length of the latus rectum is given, no matter if it's in the y-squared form of the parabola or the x-squared form of the parabola, the latus rectum is given by the absolute value of 4p, okay? So the reason you're taking an absolute value is because you're talking about a length, and if you have negative values, and you're talking about length, that doesn't make sense because there's no such thing as a negative length. That would be like imploding on yourself or something. So we take the absolute value of it to garner a positive value from it. So that's really all that you missed, is that the length of the latus rectum is the absolute value of 4p. Okay. Now, I'm going to erase this whole slide because we're going to work with the problem that was originally on the slide. Okay, so now we're ready to find the focus and the directrix of this parabola. Notice this one's going to be a little bit different because we have x squared as our form of the parabola. So I'm just going to write down the information that you need to know about the x squared form of the parabola, and that comes as x squared equals 4yp. And when you're in the x squared form, your focus is given by 0p, and your directrix is given by the equation y equals -p. All right. And then I'll also say that the length of the lattice rectum is given by the absolute value of 4p, because we will need that for this particular problem. Okay, let me go back down to a smaller pen here. Okay, so we'll start the same way. We're given in our general form that x squared is equal to 4yp. So I'm going to take that 4yp and plug it into the equation for x squared to begin solving for p, just like we did with the y squared version of the parabola. So I have 4yp is equal to negative 12y. So I'm trying to solve for p. So I need to divide off 4y from both sides. And I end up with p is equal to negative 3. So since your p is negative, this is going to open downward. All right. We can go ahead and talk about what the focus is. The focus is given by 0p, so that's 0, negative 3. The directrix is given by x equals negative p, so x equals negative 3, or x equals 3. All right, I'm going to go ahead and show my directrix. My directrix is, oh, no, I'm sorry. This is y equals negative p. Let me correct that. Sorry about that. I was about to say this is supposed to be a horizontal line, and that is a vertical line that I have written there. So this is y. Y equals 3. Okay, now I'm ready to graph my directrix. So that is a horizontal line going through the y-axis at 3. All right. And my focus is 0, negative 3. Right there. Once again, because we're centered at the origin still, I can go ahead and mark my vertex at the origin. And we will graph the other 2 points using the latus rectum, so I can show you how to do that. Okay, so the length of the latus rectum is the absolute value of 4p. In this case, that's the absolute value of 4 times negative 3. So here's one of those cases why we need to be using the absolute value for this. Okay, so this tells me that the length of my latus rectum is 12 units. Let me show you what that means. I'm going to get a really skinny pin here. That means from my focus that I will move 6 units in each direction to hit the parabola. So I know this is a point on the parabola, so 6, negative 3, and then 6 units in the other direction, right there. So the length of the latus rectum is 12 total units. That's why I halved it for either side there. And so we've got 3 points. We are ready to graph our parabola. And that's it. Anybody have any questions about that one? Give me a green check if you're ready to move on. Okay, it looks like we have unanimous decision to move forward. And it brings us to another problem to solve. And I tried for the life of me to get Word to let me put a point on the focus, and it wouldn't, so I'm going to go ahead and put a point on the focus. And that's given up here. So your focus is 8, 0, and your directrix is -8. Okay, so we are asked to find the standard form of a parabola that has the focus 8, 0, and the directrix x equals -8. Now, even if I didn't have a picture here to look at, I would know that this particular parabola opens left or right. And I could actually deduce that it opens to the right by solely looking at the directrix. That is a vertical line. So it's going through -8, and if that has to be on the outside of the parabola, then you know your parabola has to be opening to the right. Because if it were opening left, it would contain the directrix, and we know that's not how these things are built. And you can also look at the fact that the focus is +8, 0. So looking at both of those, even if you didn't have the picture, you would be able to tell that this is opening to the right. Since this is opening to the right, right or left instead of up or down, we will use the version of the equation y squared is equal to 4px. So just as a reminder, when you have the y squared version, your focus is given by p, 0, and the equation for your directrix is given by x equals -p. Just as a reminder for you. Okay, so we are trying to write y squared equals 4px for this particular parabola here. Well, I already know what p is. I know what p is because it's already showing up in my focus and in the equation of my directrix. So p is equal to 8. I can go ahead and fill that in. Y squared equals 4 times 8 times x. Y squared is equal to 32x. And that's it. It feels like it should be harder than that, but you've got your equation in standard form there. Any questions about that? Probably just a big fat smile that that's so easy. Everybody good? Green check, green check, green check, green check. Excellent. Okay. I don't know if I'm going to meet my goal of being done before 6, but we don't have too much further to go. Okay, so that all the information that we've talked about was when the parabola's vertex is at the origin. Now, of course, we have to look at other cases when it's not at the origin. And all of this stuff should look awfully familiar to you by now. So we have the good old HK. H always goes with the X. K always goes with the Y there. So you have this first version. This is the Y squared version. So you just have Y minus K squared equals 4p times x minus h, and just vice versa for the x squared version of it. Now, I do want to point out that just like we had with the ellipse and with hyperbola, minus is in the form. So if you see a plus inside the parentheses there, you've got to flip-flop your thinking and say, oh, that came from minus a negative. So for example, y plus 3 squared equals 4p times x minus 2. This is the same thing as y minus negative 3 squared equals 4p x minus 2. So hk in that case right there would be 2, negative 3. And let me highlight where that 2 and that negative 3 came from. Here's the k, and here's the h. So, is everybody good with that? And then, of course, you know, your directrix is going to have the h involved if it's x equals, and the k involved if it's y equals. Your focus has it added on to either the x or the y. Once again, this will be a really good page to have sitting in front of you when you take your test. How many times have you had a professor encourage you to have your notes sitting in front of you when you take a test? That should feel good. Okay, so let me find where I am with my notes. There we go. All right, so we have a parabola here that is not centered at the origin. And right off the bat, the thing that jumps out at me is this plus sign right here, because I know it should be a minus. So I'm going to go ahead and just start out by rewriting this equation. X minus 2 squared equals 4 times y minus negative 1. I almost said squared, but it's not. It's just that single variable on that side of the equation there. Okay, so we can go ahead and say HK in this case is equal to 2, negative 1. Remember, H always goes with the X, K always goes with the Y. Okay? All right, so from there, we know in the general form, which I'll write the general form for you so you can have it to look at while I'm blabbing at you. I'll write it at the bottom here. This is the x squared version of the parabola here, so it's x minus h squared equals 4p times y minus k. So from that equation, we know that this 4 right here has got to be equal to 4p here. So 4 from the equation equals 4p from the general form of the equation. Hope I didn't lose anybody there. Please stop me, raise your hand if that just threw you for a loop. Other than that, I'm going to keep on. Okay, I see Courtney's typing, so I'm going to hold off for a moment. And I should have color-coded this better. Let me recolor code it. It might answer your question. Will there always be a 4 in the equation? No. And we'll see an example. So say, hypothetically speaking, say my equation had been, let me get off to the side here. Just say my equation had been x minus 2 squared equals 16 y plus 1, that 16 would be equaling 4p. Now 4 is always in the standard form of the equation. But in the actual equations that you encounter, you may not see a 4. And you've got to get that factor of 4 out because it is in the general form. Did that answer your question, Courtney? Great. We'll move on. Okay, so once again, I'm trying to solve for P. So I divide 4 off of both sides, and I'm left with 1 equals P. Okay. So actually, I shouldn't have written HK at the top because HK doesn't apply since we're not centered at the origin. What I should have written was for the x squared version that is not centered around, well, HK is the vertex, but the focus is where. So HK is the vertex, which is 2, -1, but our focus is given by HK plus P. So from that information there, my focus is given by H, which is 2, K plus P. So -1 is K, plus 1 is P. So my focus is actually 2, 0. My directrix, I'm just going to put direct, is given by Y equals K minus P. And all of this information is on that last slide, and it's in your notes. So for this particular parabola, I have Y equals K is -1 minus P, which is 1. So in this case, Y equals -2 is the equation for the directrix. So let me go ahead and put my focus and my directrix on the graph. And actually, we've already answered part of the problem here. We wanted the vertex, which we got, the focus, which is here, and the directrix right there. Now we're ready to graph. So my directrix is Y is -2. That is a horizontal line going through the Y-axis at -2. My focus is 2, 0. Oops, wrong way. No, that's right, 2, 0. So my vertex, I'm going to do this in a different color. My vertex is 2, -1 right here. And I can use the latus rectum to get the other 2 points, because remember it goes through the focus equidistance either way and hits the parabola. So I have 4P, or absolute value of 4P. Absolute value of 4P in this case is 1. So 4 times 1, which is just the absolute value of 4, which is just 4. So remember, I've got to half it both ways. So 2 in one direction, 2 in the other direction. And that puts a point at 4, 0 and 0, 0. And now I'm ready to graph my parabola. So there you go. a parabola in x squared form, not centered at the origin. Give me a green check if you're ready to move forward. We've got 2 slides left. Okay, 1, 2, 3. Courtney, you got there we go, 4. All right. Now we should be back on track with the notes. Okay, so you are given an equation of a parabola in a nasty, nasty form. So we have to go through the process of completing the square to work with this particular parabola. So I'll start that process. When I complete the square, I want y squared and y on one side of the equation and everything else over on the other side. So y squared plus 2y, I'm going to leave a space for the completing the square part. Welcome, Kwame. And I would have to subtract 4x and add 7 to both sides to get it onto the right-hand side of the equation. So negative 4x plus 7. Now, completing the square, remember, all you do is add b over 2 squared. So b in this case is 2. So I'm going to add 2 over 2 squared, and I can't just do it to one side, it's got to go to both because it's an equation. All right, so I'm just going to simplify here. Y squared plus 2y plus 1 equals negative 4x. Okay, so this is 7 plus 1, which is 8. Now that I have the left-hand side as a perfect square trinomial, I can turn it into its factored form, and I purposefully completed the square so that I would know I have y plus 1 squared there. And that equals negative 4x plus 8. I know that I need to pull a factor out to begin looking like the general form for the y squared parabola. So I would have to factor out a negative 4, and that would leave me with x minus 2. So now I look like a parabola. My next task is to try to figure out what p is here. So we know that this part in the equation is represented by 4p. And I'll just write that general form of the equation for you again. This is the y squared form of it, so I'll write it at the bottom. It's y minus k squared equals 4p times x minus h. So that negative 4 is equal to 4p. So 4p is equal to negative 4. Divide 4 off of both sides and I get p is equal to negative 1. Now I can start moving towards my focus and my directrix. I can also see from that final version of the equation right here, remember this y plus 1 right here is really y, so let me delete that off, is actually y minus negative 1. And then I have a 2 in the position of h. So my vertex is 2, negative 1. My focus is given by h plus p, k. So in this case, I have 2 plus -1 and -1. So this first -1 is p, the second -1 is k. Need a mark there. All right. So that simplifies to 1, -1 for my focus. And I forgot to put a graph on your note sheets and on the slide to actually graph this thing, but I'll just draw a graph and y'all can laugh at how bad it looks. All right, and the directrix is given by the equation x equals h minus p. So x equals 2 minus -1. So x is 3. All right, I have everything that I need except for my latus rectum, which we'll find in a moment after we begin graphing. So I'll just draw a graph here. This is going to be bad. Y'all can use your imaginations though. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay. So my focus is 1, -1 right here. My directrix is x equals 3. And let me get a different color for the vertex. The vertex is 2, -1, which should make sense since it's got to lie directly between the focus and the directrix. Now we just need to find a couple other points, and we'll do the endpoints of the latus rectum. So that's absolute value of 4p is equal to the absolute value of 4 times -1, the absolute value of -4, which is 4. Okay, so since this particular parabola is situated so that it's going to open left, we actually want to move 2 units up and down from the focus. So 2 units up from the focus is at 1, 1. 2 units down from the focus is 1, -3. And I'm ready to graph. All right, that's pretty bad looking, but hopefully it made sense to you. Give me a green check if everything's cool. And we've got one more problem to go through, the application problem. Mike and Kwame, are you still with us? Okay, I'm not getting a response, and I'm not seeing that either of them are typing anything, so I'm just going to assume they're good. Okay. All right, so our application problem. And by the way, the pictures at the bottom of the last slide were just practical pictures of how parabolas are used in everyday life. So we had bridges, both an arch bridge and a suspension bridge, and then they're also used in reflecting light. So in lights and mirrors and things like that, they'll use parabolas for reflecting light. All right, so in this case, an engineer is designing a flashlight using a parabolic reflecting mirror and a light source. The casting has a diameter of 6 inches and a depth of 4 inches. what is the equation of the parabola used to shape the mirror first, and then secondly, at what point should the light source be placed relative to the mirror's vertex? So the first thing we want to do is put this on a grid. And it would be preferable to have your vertex at the origin because that's a heck of a lot easier to work with. So I'm just going to draw an X and a Y axis so that the vertex of my parabola is centered at the origin. In doing this, we now know I can give names to this point here and this point here. Now, mind you, this parabola, in theory, keeps going. But the reason I can give names to those points is because I'm given measurements. So I know that this thing is 4 inches high, and I know that the diameter of it is 6 inches across, so it's 3 inches in either direction or on either side of that y-axis. So this point right here has the coordinates 3, 4. And this point on the other side is -3, 4. So that's everything we can label so far about our parabola. Now we know that this parabola is going to be in the form of x squared equals 4py because it's centered at the origin and it's opening up. So we use the x squared version of the equation. And I already have a couple of points that I know are on the parabola. So I can plug one of those points in to the equation for x and y, and it will allow me to be able to figure out what p is. So I'm going to plug in 3 for x and 4 for y. And that gives me 9 equals 16p. And this is going to be a not so feel good p-value. Divide both sides by 16. And we get p is equal to 9/16. Okay, so not feely good at all, but it works. Okay, so now that we've used that point that we knew to get p, we can start filling in pieces for the general equation. So x squared is equal to 4. I now know that p is 9/16, and I multiply that by a y. So let me just show the math here so it doesn't look like magic to you. 4 goes into 4 once and into 16 4 times. So I'm left with x squared equals 9/4 y. There is the equation that I'm looking for. And then we're asked to tell where this light source needs to be. Well, the light source needs to sit at the focus. If it sits at the focus, it's going to have maximum amount of spreadage, if that's a word, through that parabolic reflecting mirror there. So all we need to do is figure out what the focus is to know where to put our light source. The focus is given by 0p. So my focus in this case is 0, 9/16, which tells me to answer the question, I need to place the light source 9/16 of an inch above the vertex. So that answers both of the questions. And that's all I have except for the last slide that's going to announce the next lecture, which is tomorrow morning at 7 a.m. So does anybody have any questions about this application problem? Okay, it looks like everybody's good. Oh, Peter's typing. Okay, great. Let me go ahead and show this last slide, and then I'll let you gentlemen get on out of here. Okay, so the test review is tomorrow morning at 7 a.m. I will pull specific problems that will look a lot like what you're going to see on your test from 9-1, 9-2, and 9-3. I usually pull about 10 to 12 problems to look at. Your test is 30 problems. There are 10 problems from each section. And that test will be due Monday by 11:59 p.m. So if you gentlemen are good to go, I appreciate you hanging in there with me a little past 6. And happy studying this weekend. Let me know if you have any questions. I'll be doing taxes this weekend, so I'll probably have my email open wishing for somebody to email me so I can stop doing my taxes. Thank you, Roy. You have a good night, too. When's the test? The test is already out there for you, Kwame. You can go take it now if you want to. I would wait until after I do the review, and you either watch the review online recorded, or you can join me tomorrow morning at 7 a.m. The test is due to me. It must be completed by 11:59 p.m. Monday, February 2nd, which is this coming Monday. So you've got through Monday at 11:59 p.m. You're welcome. Have a wonderful evening. Thanks for joining us.